So there will be 3 parts. One of them is going to be an explanation of why extra dimensions actually occur in physics in the first place. And then I am going to talk about 2 different types of using extra dimensions, or 2 different ways in which extra dimensions occur in physics. They both, neither of them actually, I should say, has a very definite word, catchphrase, except compactification got really popular over the past, let's say, 15 years or so among the people who are doing this. Among the people who have never heard of this, probably you don't know what compactification really means, so hopefully this will be a little bit clearer. Embedding is a word that I borrowed here from mathematics simply because nobody came up with a better terminology yet, and somewhere down the line, history tends to be very capricious. Sometimes words latch on and they show up in a Nova show or something, and all of a sudden the whole world is abuzz with the term, and it's not really the right term, but then it gets stuck and everybody starts using it. Well, right now there's no particular word for this other kind of use of the extra dimension, so I'm just going to use embedding. And the last bit is going to talk about brane world cosmologies. Brane world has nothing to do with Wayne's World, by the way, for those of you who know what I'm referring to. Brane world has something to do with membranes, except they're not membranes, they're not sheets. They're a little bit more complicated than that. And they actually describe, well, cosmology, so ways of possible configuration of our universe and possibly other universes that might be adjacent to ours, or bigger universes of which ours is a part. And as you can see here, there are going to be some names that you know very well: Maxwell, Lorentz, Minkowski, Einstein, Nordstrom, Kaluza, Klein, and then also Rundle and Sundrum, which are definitely newer words, newer names. And then for the last one, I don't really have any particular names to report on, so I just said allegro con brio, which means sort of vividly with much oomph, let's say, translated like that from Italian. So first of all, Maxwell's equations, which by now you get on t-shirts, and they are kind of public knowledge. In some notation, they can be written like this, and you may have noticed this additional piece is in green, because I don't know how many of you have followed, maybe about 2 weeks ago, there have been some recent reports that magnetic monopoles have been found. Well, they're not quite the magnetic monopoles that Dirac has thought of, but they're kind of like that, and in certain circumstances you can think of those things that have been found in laboratories as the magnetic monopoles of the kind that Dirac described. So depending on your application of the Maxwell's equation, you might want to make them more symmetric. As you can see, when you include those green terms, then this and this looks very similar, except for some changes in where these constants are included, whether you divide or multiply by a constant just to make units match. And also this equation becomes much more symmetric with a noted minus on one side. So up to these issues about units, for which you need the epsilon 0 and the mu 0 here, the pairs of equations on the left-hand side and on the right-hand side become very symmetric. But aside from that symmetry, this set of equations has some, first of all, they can also be written in a more compact notation that those of you who will learn physics, or have already learned physics maybe, you've been tortured by your professors, maybe like Kostas, using the 4-vector notation, and then everything gets kind of compacted into a nice form with these indices. And again, this green term is here for the magnetic contributions. If you want to include them, then again, these 2 equations become, well, almost identical, except for this epsilon sitting there. But the point is that these equations exhibit some symmetries other than just the obvious left-right symmetry, which, by the way, we sometimes actually refer to as duality between magnetic and electric charges. It has continuous symmetries. They are called Lorentz symmetries. They include rotations. They include also some things called boosts. And in particular, the way these transformations look like, this is going to be about as much mathematics as you will ever need. Most of it is going to be in pictures, by the way, so don't get scared away. So these quantities, this f mu nu, they're not just so that some instructor can torture you of how to change from the usual three-dimensional vector notation into this four-dimensional notation that is kind of hard to wrap your mind around. But it's simply because once you rewrite these equations in this much simpler way, it becomes almost instantly obvious that these equations have some larger symmetries. In particular, you can think of this as a matrix where one index and the other index are labeling columns and rows. 1, 2, 3, 4 columns, 1, 2, 3, 4 rows. And then you can think of transforming that matrix into another matrix by means of this adjacency transformation multiplied from one side and from the other side by a transformation matrix. And the components of this matrix then can be continuous functions. But not only does this f mu nu object transform, which actually ends up transforming the electric and the magnetic fields one into another. By the way, that's the real reason why we don't talk about electricity and magnetism much separately, but electromagnetism. It's really a single unified subject. It also has this property that it ends up transforming also the space and the time coordinate, and not just by rotating space coordinates one into another or maybe translating space coordinates, but also mixing up space and time. And this is something that, well, it comes out of these equations. These equations we know describe Gauss's law for the magnetic field, and so on, Ampere's law, and so on and so forth. These are laws. These are physics laws. So these physics laws tell you that there is a symmetry, and this symmetry forces you to bind together space and time into a single object. Well, so that's how it is. We have to get used to it, I guess. And that's what we start talking about, space-time. Well, have you ever heard of the Cheshire Cat? You know that the Cheshire Cat comes up with a smile. This is the lesser-known cousin of the Cheshire Cat. This always comes up with a frown and always complains about things. In particular, why should we bother combining space and time? Isn't space three-dimensional space, you know, up, down, left, right, front, back, good enough all by itself? And then time, well, time I read off on the watch, right? Why should I bother unifying those things? Why should I bother saying that we talk about space-time as a single entity? Well, what's the alternative? Well, the alternative is relaxing the Lorentz symmetry of those Maxwell equations. So allowing terms in the equations, add some more terms, which are no longer going to be Lorentz invariant, so invariant under all those transformations or those changes of space and time. So look at a restricted set of transformations called the Galilean Transformations, which don't mix space and time. So this would be the more maybe mundane, everyday experience that we have. You never see us somehow walking and then all of a sudden walking into time. You always walk in space as some time is passing, right? So you don't really see very obviously this transformation of space into time. Well, so can we kind of reverse physics laws, add some more terms maybe in those Maxwell's equations, which are not then allowing these extra symmetries, see what happens. Well, unfortunately, nature has something to say about that, which is no way. Those additional terms, and you can check out, there are several additional terms which you could add into the Maxwell's equations. They represent just physical nonsense. There is no such thing. You cannot have the equations, Maxwell's equations, modified in such a drastic way, so you just have to accept them. But that also means you have to accept a logical conclusion from that therefore electromagnetism is symmetric with respect to this transformation that does mix space and time into space-time. But that's not all. So in the beginning of the 20th century, so that's a good 100 years back, I said this is going to be a little bit historical in that sense, but maybe not quite the history that you've had in high school, or probably not something that was mentioned even in your physics classes. We've had this nice theory of Maxwell's equations that completely describes electromagnetism. There was another theory that was developed, initially started off in 1905 as special relativity, but then by 1926, so not quite the quarter of the century, a little bit year above that quarter, was completed into something that we refer to as general relativity, which does explain gravity. And by the way, as you will see soon, there were a couple of other competing versions of explaining gravity. Notably, there is Newton's theory of gravity, but there were a few other ideas what might one do beyond Newton's theory. And most of them boil down to whether or not a certain particular experiment would come out to say one way or the other. In particular, objects rotating around a very heavy mass, such as the sun, and the closest object that we know and can observe that rotates about the sun is Mercury. Mercury is supposed to not rotate on an ellipse that stays stationary in space, but it's supposed to precess. It's the orbit itself, if you like. Think of the longer axis. That longer axis is supposed to itself rotate about the sun. And the rate at which it rotates is supposed to be predicted then by the theory. And there were several different ideas how that might work. The idea was, well, it had to be then observed, and lo and behold, of course, as many of you may have read about this in some textbook, it was observed that indeed that precession of the perihelion of the Mercury turned out to be in agreement with Einstein's theory. That was a bit after the first quarter of the century. There were also some other queer quandaries about quantum mechanics and some pesky peculiarities that people started noticing, but which was still far away from a good description of what we nowadays call nuclear physics. Remember, we're talking about 1920, 1925, maybe 1926. So the idea was, well, can we somehow put these two things together? And, you know, theorists be theorists. Wouldn't it be nice if electromagnetism and gravity were somehow joined into a single theory? And what might be required to do that, to accomplish that? Now notice that just because the metric, this metric tensor that occurs in Einstein's theory of gravity, some of you may have seen. So for those of you who have seen these mathematical symbols, you know what they are. For those of you who haven't seen the symbols, just think of them as placeholders associated with, in this case, gravity. Just because this thing is symmetric when you swap the indices, it's like a matrix that when you flip it about the diagonal, it turns out to be the same thing. And this other matrix, the F mu nu, that is a hallmark, something that's used in electromagnetism, when you flip it about that diagonal, it turns into negative of itself. So we call this symmetric and this antisymmetric. You can, of course, put the two together, but that doesn't make a new theory, just because you could put these two matrices together. We need a little bit more than that. And so a couple of people had some ideas about it, notably in 1914, which was not a very good year for publishing papers, because certain other things were happening in the world. This gentleman, Gunnar Nordström, had an idea about how that might be achieved. He also developed this in his own version of gravity theory, which turned out to be a competitor of Einstein's theory. So the sort of ghost of Einstein lingered on and eventually beat him. So that's why we don't teach Nordström theory of gravity in schools today. And then there was this other gentleman, Theodor Kaluza, or Kavuja, I think how this is pronounced. His name is of Polish origin. He submitted a paper actually to Einstein in 1919 for comments. This was an idea, which I'm going to describe in a minute, how electricity and magnetism on one hand and gravity on the other hand might actually be unified and what it might take. It turns out Einstein actually liked the idea, but those were much more relaxed times. So the paper eventually got published in the Proceedings of the Prussian Academy of Sciences or something like Royal Society maybe, in 21. So it was about a 2-year lead time. Currently, if we submit an article and it's not published within 6 months, we are getting edgy about it. And why is it not published? You know, why does the referee not like us and all that? Well, in those days, 2 years apparently was a very, very quick response. At any rate, there was one other gentleman, Oscar Klein, who independently, quite a few years later, had a very similar idea, worked out a bit more details. So nowadays, we refer to this as the Kavuja-Klein theory, because unfortunately, as I said, Nordström, even though the basic idea is the same, the physics idea behind it is the same, he developed it within the framework of his own version of gravity, whereas these other two gentlemen here developed it within Einstein's version of gravity. And of course, we nowadays accept Einstein's theory of gravity because it has this minor technical benefit of agreeing with nature, in particular that precession of the perihelion of Mercury. And we do not accept Nordström theory because it does not agree with that. So we'll call it the Kaluza-Klein theory, although I'll try to sneak in the word Nordström in there. In this theory, the idea is that our space-time, now space-time, so 3 dimensions of space plus 1 dimension of time, that mathematical space is supposed to be kind of part of a bigger space. There ought to be one more coordinate. So a 5th dimension, if you like. And this almost sounds like something from the Twilight Zone, but remember, Rod Serling was not even in thoughts at that time yet. So there is something that we call this metric tensor. It occurs when you want to define how to measure distances. You know, of course, how to measure distances in order on the piece of paper in 3 dimensions. You use Pythagoras theorem. But if you have coordinates that are not Cartesian coordinates, that are not straight forward to the left, straight up, but you use, for example, spherical coordinates that, you know, curve around like with an angle or something like that. If you use curvilinear coordinates, then you need to know this object here, this Gij, to compute little distances from one point to another and then integrate them, add them up along a curve. So that's something that you need in any other geometry other than the Cartesian coordinates. And in their case, you had 5 coordinates, 0 for time, 1, 2, 3 for the normal space, and then 4 for this 5th dimension. What happens is that this object, where the 2 indices, if you like, think of this as a matrix, and then that matrix chop off the last entry, the last column, the last row. So what is left is a 4x4 matrix, which is the usual metric for the 4-dimensional space-time. This is how you measure distances of sorts in space and time, kind of conjoined together. And then you have that 5th column. This almost sounds like a reference to Franco and the invasion of Madrid, if some of you know what I'm talking about. But anyway, the 5th column in that matrix and the 5th row, each of them has 4 entries. So that's what I labeled here G mu 4. And then there is that last piece, the one that's in the 5th column and 5th row, that last entry. So that's the G44. So you end up with these 3 new entities. And it turns out that when you take this mu, the mu can take values 0, 1, 2, 3. And so if it takes the value 0, that entry in that 4th column, that can be identified with the scalar potential. The next 3 quantities can be identified with the vector potential. And those of you who have seen those previous Maxwell's equations in some textbook probably were told that they can also be rephrased. They can be rewritten, translated, if you like, from the usual notation of electric and the magnetic field into a fairly usual notation also in terms of the scalar potential and the vector potential. So if they told you how to find the scalar and the vector potential, every undergraduate student who has had electromagnetism by this point will know how to compute the electric and the magnetic field from these guys. So that's, of course, what they also knew at the time. And that's how you end up with electromagnetism. Now, not only do you get the quantities to count them, the right number of quantities, but in fact, Einstein's equations, when now generalized to this 5x5 matrix, and then isolating what do those equations say about this piece that you identified with the scalar potential and about this piece that you identified with the vector potential, they actually turn out to be Maxwell's equations. So in this sense, Einstein's equations in this 5-dimensional space, 0 for time and then 4 more spatial dimensions, actually Einstein's equation, which are relativity, they give you Maxwell's equation. So all of a sudden the whole thing gets combined. It's just one theory. You only need to know general relativity, but in 5 dimensions, not in 4. And out of it you get both the 4-dimensional space-time general relativity, like Einstein's, plus you get Maxwell's equations. Well, this is kind of a nice benefit, a nice boon, and this was their primary motivation. But one thing had to be done. That 4th coordinate had to be assumed that it's not big. It doesn't extend forever in both of its directions, but rather at every point of the usual 3-dimensional space, at every instant in time, you have a little loop, a little curl, associated with that extra fourth dimension. So the extra dimensions were kind of loop-like. At every point you have additional loops. Now, if you ask anybody, even very early in the morning when it's kind of blurred what is dream and what is reality, all of us will tell you, no. There are no little loops everywhere around me. You know, I have to be really drunk to see some loops around me. But you know, all kidding aside, we know that there are 3 dimensions of space and, okay, the 1 dimension of time, and we may perhaps agree with that idea that we have to somehow combine these two because of those symmetries in the Maxwell equations and then general relativity and all that. But this 5th dimension is kind of, well, loopy. It's kind of strange, right? Well, but it is a mathematical model that does describe what needs to be done. So I was going to describe a little bit more what does this Nordstrom-Kaluza-Klein compactification entail. So first of all, I said that you have to extend the 3+1 dimensional space-time into 4+1, so a total of 5 dimensions. Then that extra 5th dimension is curled up in a circle. And again, the little curmudgeonly kitty shows up and complains about it. And well, the circumference of this circle, it must be very small if I'm not able to detect it directly. See, if it was something on the order of even, you know, 1 foot or 2 feet, I'd be able to kind of curl around it. If it was much smaller than I can possibly touch or detect in any particular way, well, then that would probably explain why I don't see them, right? In fact, we'll get back to this with another cartoonish sort of picture. But right now, let's see what else. This idea of compactification, by the way, that you have a direction of freedom, a dimension into which perhaps some physics could be extending, yet it's somehow curled up. So what does it really mean that something is curled up? Think about something that you've probably seen. Any of you been in an amusement park where they make you go through a large tube that rotates? No? Okay. So you know that there are such things. Okay. So if that thing is static, of course, the idea is that it's rotating and you have to kind of make your way through the whole thing. But if it were static, of course, you can picture yourself moving along it. Or you could perhaps stand, and if you're very careful as it is rotating, you could be walking against the direction of its rotation, so that effectively you're standing still and the whole thing is rotating. And if you were tracing out your steps, let's say you had some ink on your shoe soles, you would see your ink steps going all around that loop, right? So you can picture yourself moving in that loop. Of course, the loop has to be bigger than you are. If the loop is much smaller than you are, then, well, you just can't fit into the loop and you cannot loop around it. In other words, it would look as if there is no such loop. But let's think about systems or where you can see that loop, such as in that amusement park. Or think about it alternatively. Let's say you have a little bacterium or something that somehow developed intelligence and is now seeing that loop. How would that loop look like? Just like when you're walking in that big tube, if you were walking just so as it is turning, you would start seeing your footsteps over again. Just like in that Winnie the Pooh story where they end up going around the bush and start seeing their own footsteps and think that there is a weasel or something coming, right? So you would see your own footsteps. The bottom line is, as you keep going in the same direction, after a while you get back to where you started from. So how do you know that you got back to where you started from? Why? Because everything looks exactly the same, right? But there are things like that in real world. And not, by the way, in Twilight Zone. A crystal of salt. How does a crystal of salt look like? I tried to draw a picture here, and this is just a two-dimensional rendition where you can decide whether the salt is yellow or it's the sodium. I mean, the chlorine is yellow or is it the sodium. One of them is yellow, the other one is purplish. And if you go in any one direction, sooner or later you hit another, let's say, sodium atom, and then you go through the chlorine, and then you hit another sodium atom. So if you move in any one direction, that way or this way, if you move long enough, all this crystal will look exactly the same to you. We call this a periodic lattice. But the mathematical description of a periodic lattice is exactly as if you took this point and this point, connected them together, and made them into a loop. For the purposes of an electron that's passing through, it will look indistinguishable. The electron cannot tell one of those sodium atoms from the other one. As soon as it hits another sodium ion, to be proper, it will seem that it's back at the same place. And then it goes a little bit further, it hits another sodium atom, I'm back where I started from. I'm moving in a loop, right? So that's exactly what a concrete physical representation is of something that mathematically can be described as compactification. And I'm sure nobody ever wondered about how come salt. Salt isn't so strange after all, right? Now, the physical concept of dimension, this business about loops. So let's say that you are on some sort of modern designed kind of an armchair thingy that looks like a big cylinder that's curved up, so you can sit on that. You would definitely decide that the surface, this perhaps lumpy surface, is a surface, right? You would say that this is a two-dimensional surface. It has length and it has width. Well, if somebody made that a really teeny, let's say about 1 inch or half an inch or so wide tube, you would perhaps still think about it as a surface. After all, if you know about tightrope walkers, so if a tightrope walker was walking on one of those garden hoses, practicing for their big act, you would still say that they're walking on the surface of the garden hose, right? But if you made that garden hose extremely tiny, in fact, we're talking about 10 to the minus 35, that's 0 and then 35 zeros and then a 1 meters. If you made that really, really, really tiny, you would be very hard-pressed to call that a surface. You would call that a line. By now, it only has a one-dimensional extension. There is no thickness to it anymore to speak of. So this is the sense in which the dimension of a physical object is a relative notion. Relative to what? Well, obviously, relative to observer. If the thickness of the object, if the size in a certain dimension, the sectional size or maybe curvature of an object is appreciable from the point of view of the observer, so compared to the average size, to the average resolution, I can see very well without my glasses. With my glasses, the resolution of my eyeballs is pretty much better. Some of you will experience that sooner or later as you age. So if you can appreciate that there is a second direction, you will call it a surface, a two-dimensional object. But if you cannot, you will call it a one-dimensional object. So this is why I say that physically the number of dimensions is a relative notion, relative to the size of the observer. So in that sense, that little loop, that fourth spatial dimension, will have to be curled up and too small, so then the whole space-time will still appear to be only 3 plus 1 dimensional, which is what we observe in everyday life. So this is a way in which that extra dimension, in this case the fifth dimension, could be in some sense masked. If it's still, it is still useful because Einstein's equations still apply and they know about the fifth dimension. And in fact, in some ways, when you do the detailed mathematics, the size of that extra circle will matter. The actual size will tell you what is the relationship between the electromagnetic coupling constant or charge and the gravitational coupling constant, or what we call mass. It will give you a relationship between that. And in fact, we will have to use a very small size for those circles. But it can be done, and that's the point. So that's your first example of extra dimensions. By now, so this was, let's say if you take some sort of a average between 1914, 1919, and 1926, let's say we take that 1919, then it makes the idea 90 years old. So 90 years ago, you've already heard about extra dimensions. People just haven't been popularizing them very much. So it's with a little bit more modern understanding, the extra fifth dimension should be curled up and the circumference should be smaller than 10 to the minus 33 meters. The fields, those components of the metric that we need to analyze here. They also decompose into something called Fourier modes. And some of you here may have had some mathematical course in which you analyze things in Fourier analysis or did Fourier synthesis. But I'm sure that everybody here has at least heard a guitar at some point and seen a guitar. So you know how the string vibrates. And if you can almost see it smeared a little bit when somebody plucks it. And you can see that the smearing of that guitar, it actually takes different shapes depending on what kind of tone you play on that guitar. It doesn't always do just this. It does some interesting kind of motions. And those different kinds of motions are referred to as different Fourier modes. So we will have to do that. And as you can tell, there is a bit of interesting mathematics coming out of here. Well, in one dimension, this is very easy. In more than one dimensions, which people started doing in the latter part of 20th century, this does become much more difficult. And we're not going to go there. The rest mass of this nth mode, each of these modes behaves like a particle. And the mass of this particle, the thing that you would observe by trying to push this particle, and then the particle will accelerate with some coefficient of proportionality. The more, if I push with a certain force and I measure how much acceleration it produces, the ratio between those two gives me how much inertia the object has. That's what we refer to as the mass of the particle. It will be proportional to this coefficient, which has the integer n in it, depending on which mode I'm talking about. And the mass itself is 10 to the 17 giga-electron volts per speed of light squared. That's a kind of unit that is often used in particle physics. It's actually not very big compared to, let's say, a gallon of milk. But it is extremely large compared to elementary particles. Elementary particles, like an electron, don't even have giga-electron volts, is 10 to the 9. And in some earlier versions of this talk, I could say, this compares to the national deficit. But, well, by now the national deficit dwarfs it. But GeV, that's 10 to the 9, an electron has the mass of a mega-electron volt. So about 1,000 times less than a giga-electron volt. But then there is this pesky 10 to the 17. So 1 followed by 17 zeros. It's much, 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 much larger. Okay? Now, here is another point of view why we might need extra dimensions, but now those very teeny ones. So here is a cartoon I found. Rescue crews were called to the water spout today as the spider formerly known as Itsy Bitsy attempted to relive his glory days. And you can see Itsy Bitsy being stuck in the water spout. Here is a little hermit crab trying to get into some of the former sheds and says, "Who am I kidding? I'll never be able to squeeze in those again." So if there were some extra dimensions, some of us who are, concerned about extra weight would have some extra dimensions to spread out. So that would be kind of nice. So that's why I said, who are you kidding? We need extra dimensions. All right, let's get back to more serious stuff. Or maybe not, depending on how you think of superstrings. But I happen to work on superstrings. So here is the reason why superstrings actually do need extra dimensions. I'm not going to go into details. There will probably be some other speakers who will talk more about superstring dynamics. But the bottom line is that one way or the other, superstrings require 10-dimensional spacetime. So not 4-dimensional, not 5-dimensional, but they require a full complement of, 10-dimensional spacetime. 1 time, 9 space. Well, so we have to kind of curl up those extra 6 dimensions. And in 1984, Candela, Horowitz, Strominger, and Witten wrote a hallmark paper in the latter part of 20th century where they actually showed if you decide to do that, if you indeed take a 10-dimensional spacetime and curl up 6 of those dimensions and expect that you get some reasonable theory out of it. So this is a sort of Kaluza-Klein geometry, but also includes something called supersymmetry. And I talked about that last year, so I'll expect you to fill out the quiz at the end of this talk. So if you combine the Kaluza-Klein geometry that those gentlemen had in 1919 and this newfangled idea of supersymmetry, you end up with a class of spaces that are called Calabi-Yau spaces by Eugenio Calabi, who conjectured the existence of such things. and Xingtung Yao, who has proven that such things exist. And their hallmark is that something called the Ricci tensor. Again, for those of you who know what it is, good, you know what it is. For those of you who don't, just file it off as a sort of placeholder. That thing ought to be 0, or rather equivalent to 0, up to something called total derivatives. Okay, so these are what are called Calabi-Yau spaces. And it turns out that a little bit after these gentlemen have proven this, and by the way, this was sort of my introduction to the field where I started constructing such Calabi-Yau spaces and learned about their geometry. A large number of people here, Frankel, Garland, Zuckerman, Rajiv, Bowick, Alvarez Gomez, Reina, Pilch, Warner, O, Ramon, Harari, and Hong. So all these gentlemen have proven in very different ways that this condition, that this thing called Ricci tensor, ought to be essentially 0, or 0 up to total derivatives. Or the way mathematicians refer to this, there is something called the cohomology class represented by this object called the Ricci tensor. That cohomology class has to vanish. Since we have mathematicians in the audience, I thought I'd put that plug in there. This is actually a superstring condition. It's not just for that particular idea when you take the superstring theory and combine it with Kaluza-Klein theory. It's true that that's how it was first derived, but it turns out to be a generic property of superstrings. It's something like the condition for strings to be consistent in the first place, before you do anything else to superstrings, whether in 10 dimensions or you curl up some dimensions or whatever else you may want to do with them. That condition has to hold. So some of us started wondering, well, okay, what might then the generic or the typical space-time in string theory look like? Well, it has to be Ricci flat. It has to have that property. And we could use a trick. We take the time dimension. Those of you who have studied a little bit special relativity or maybe even general relativity will know that when we measure distances, in ordinary Euclidean geometry, you take the square in the x direction, the square in the y direction, the square in the z direction, and if I continue with my letters of alphabet, you just add up squares. You add them. But in special relativity, the one particular direction which is in the direction of time, the square of that quantity you subtract. That's how it is. That's the quantity that is the invariant. That's the hallmark of special relativity, and then also in general relativity. That's just how it is. But there is an easy trick. If you take that coordinate, which you use to label time, multiply it by I, the mathematical unit, the imaginary unit, the square of I is -1, so that flips around the sign, and so we call that Wick rotating. If you Wick rotate what we normally call space-time, you just get usually Euclidean space. It's much easier to work with. A lot of mathematics has been developed for such things, much more so than for the other kind. So you can Wick rotate space-time into this Euclidean space, do your math there, and then Wick rotate back. Sometimes this works. Sometimes this flipping back and forth, sticking in extra factors of I, will actually violate some of the theorems that you want to borrow from mathematics, and of course then you cannot do it. You have to be careful. So beware, user beware. If you are going to try to use mathematical theorems, read their assumptions. Okay? But sometimes it does work, and you can use a number of mathematical theorems in this setting also. And then there is also another condition that it turns out most of the time when we talk about space-time, we think about nice spaces, even if they are crumpled, lumpy, strange like the surface of a potato, but they are kind of continuous. Well, it turns out that string theory doesn't actually require that. String theory is perfectly happy to live in space-times that might be 5-dimensional here, and then, oops, there is a little bit of an extra, what mathematicians call stratum, a little bit of an extra thing sticking out, which happens to be 3-dimensional, and then another little antenna sticking out of that might be 1-dimensional. So these things are called stratified spaces, and it turns out that string theory is perfectly okay with that. So you could also allow in certain direction such spaces to be non-compact. So there is again our little curmudgeonly kitty. asking, well, what's next? You know, we're just arbitrarily making silly assumptions here. Well, going back to string theory, the generic string theory, so the type of, if you were to look at the whole haystack of possibilities and take your needle and sort of pick one at random and ask how is that thing going to look like, the most probable kind of thing, well, the most probable kind of thing will have the following features. It will have something that can be shown to be isolated four-dimensional subspacetimes. So this is something interesting. Why? Well, first of all, how does that look like? Think of this, the surface of this kind of pinched donut. Think of this as a surface of a donut where I kind of, before it was fried, I kind of pinched it down to a point. And so you can see that there is a circle that goes around, but as I come closer and closer to this point, the circle becomes a single point. So in many ways, while you move this circle, there is not much of a distinction between this circle and that circle. They're getting a little bit tighter, a little bit bigger, but they're essentially the same thing. They're circles. But when you get to this special point here, the circle all of a sudden becomes a point. It's different. And in particular, if you were a bug living on the surface of this donut, you could very well tell whether you're here or somewhere away from there. You wouldn't be able to tell very much the difference between this place and that place on the surface of the donut, but you would very well be able to tell that you are over here rather than there. So there are such special places in that, in those 10-dimensional generic stringy spacetimes, and those special places turn out to be 4-dimensional. They're, for the mathematicians in the audience, they turn out to be exceptional sets of something called small resolutions. For those who know what it is, now you know. For those of you who don't know, just know that there are some special such places. Okay. Something else is true. There are going to be vibrations or modes, those Fourier modes. And you can see that on this string there are going to be interesting Fourier modes, vibrations of that loop here. But bear in mind that due to budgetary restrictions, I can only show you 2-dimensional pictures. I couldn't figure out how to show you 10-dimensional pictures. But think of this as being a 10-dimensional object and this as being a 4-dimensional subspace. Okay? So that 4-dimensional subspace will have some oscillations, some vibrations on it, and it's going to be more complicated than just what you can picture on the circle. And you can study that mathematically. Turns out that those modes are going to be different here than here. That's kind of obvious. Not only that, but you can show that the number of modes that you can find on those special 4-dimensional subspacetimes turn out to be enough to span out the things that we know we are made of, things like quarks and leptons and photons and stuff like that. So we could actually develop a theory where this big, lumpy, smushed down donut-like 10-dimensional space has a particular one or maybe more, has a particular location, a 4-dimensional location, on which there is enough of those modes to make the model, that the so-called standard model, the electrons and the muons and the up and down quarks and what have you. And we could have our world reside right there. But more than that, actually, there is something funny. So here's another rendition of the same picture. Remember, that was really meant to be 10-dimensional. So viewed from another angle, you could think of the surrounding extra space to be something like a helicoidal staircase. And the actual spacetime that we live on would be that pole that holds this extra, the rest of the stairs. When you look at it from above, the whole thing looks like a disk. And what we think of ourselves as the spacetime is just, you know, that pole viewed from above, just a point, just this little peg. Well, you could do now the following. For those of you who are interested in science fiction, I always wanted to be a scientist who will invent, I don't know if you are a fan of Star Trek, then you probably know who invented warp drive. Well, this is not going to be warp drive, but this is going to be something like those Babylon 5 jump gates, where what we need to do, we just need to figure out how to get out of our universe, make a loop around in the extra space, and come back to our space, our space-time. Because in this model, if you get out here, and you now move on the extra space, come back, you will come back at a different point in our space-time. And it turns out it is possible, in principle, at this point, that you will come back to our space-time sooner than a light signal could have passed if it was traveling entirely in our space-time. It's possible. And, so I thought in 1996, where I presented this at a conference, this is, by the way, the conference proceeding showed up a year later. And then somebody in the audience asked me, what about gravity? Can you make gravity remain in that subspace? And this is actually a tricky question. As you know all, the gravitational law, since Newton, we know that it falls off as 1 over r squared. Well, in a larger dimensional space-time, in a 10-dimensional space-time, it would fall off as 1 over r to the 8th. That would not work for our solar system to work the way it does work. So that definitely is not a good gravitational law. So the gentleman, Greg Moore, in the audience asked me, can you make gravity work in this subspace to be the 1 over r squared gravity? And I had to say, nope, I don't know how to do that. And nobody knew how to do that. And that's where this discussion stopped at that point. The curmudgeonly kitty showed up its frown again. And by 1999, a lady and a gentleman, Lisa Rundle and Raman Sundram, coincidentally, 80 years after Kaluza, or Kavuja, ended up discovering a fantastic new way of doing things. So they looked at the toy model, just for simplicity, okay? Just to work out sort of the crank. Our spacetime is a subspace of a bigger 5-dimensional one, just like Kaluza, Klein, and those guys had imagined it. But this time they're going to stick it at the boundary. In other words, it's something like a box, or if you like, parallel plate capacitor. And the bulk of the world is between the two parallel plates, but our world is on one or the other boundary of that parallel capacitor sort of picture. And there is such an example that actually comes kind of inspired from string theory. It's called the Heterotic Am Theory by Hojava and Witten. You'll see some interestingly accented letters here. But anyway, in that particular case, this is not like Rundle and Sundram pictured it. This is now actually an 11-dimensional parallel capacitor with 10-dimensional plates on each side. And it turns out that they found in this theory that in each plate, in each boundary end of the world, you actually have a whole E8 gauge group. This is quite a few years before Garrett-Lisi. And Garrett-Lisi's theory that got recently extremely popular about E8 has absolutely nothing to do with this, foremost because what these gentlemen showed, Horava and Witten, as the E8 gauge group actually could work as a theory. It had both bosons and fermions, and everything actually does work in that theory, whereas Garrett-Lisi's theory does not have that minor technicality. So that would now allow room enough for all of us. And so you could actually picture all of us actually living on one of those boundaries. And so the question then begins, remember, this is just a toy model that Rundle and Sundram developed. But here are some of the key points. And in fact, it really turns out like Prince's Song Party, like it's 1999. Because, well, first of all, these two papers that they wrote turned out to be the most cited papers in the past decade. The first paper, as it is affectionately referred to as RS1, shows that it is possible to find something I never told you yet, but it turns out to be a fantastic boon. It shows an exponential hierarchy of what? There is a certain mass which is associated with gravity, which is 10 to the 19 gigaelectron volts. This is the strength where gravity becomes confiningly strong. This is associated to black holes, if you like. And so this is a sort of hallmark energy. This is where gravity becomes stronger than anything else you can think of. And, well, so this is a characteristic parameter for gravity. On the other hand, you have another characteristic parameter. These are the masses of the weak or electroweak particles, W plus minus and Z0. This is the energy scale which we understand, at least currently in the standard model. All other masses of the particles that we know of, the electrons, the quarks, they are all proportional to this scale with some numbers that presumably someday we'll figure out how to compute. But this is 17 orders of magnitude difference. If you like, this is 17 orders of magnitude fine-tuning. If your professor caught you, there are mostly students here, if your professor ever caught you that you fine-tuned 17 digits in your answer, you can be sure what your grade would be, right? So that's not quite right, or inexplicable why there should be such a difference. And in this theory of Rundle and Sundrum, in this model, it turns out that there is an exponential relation, and it's governed, or it's driven by an exponential relation through this x4, but it's related or governed by the curvature of that extra space, not the size. This turns out to be very important. So this is one of the hallmark papers. So in the other paper, they show that it is possible to localize gravity, precisely what Greg Moore had asked me 3 years before. They've shown how to do it. So it is possible to have the bulk gravity, which goes as 1 over r to the 8th, and in the boundary to have 1 over r squared force. That's brilliant. Except in their models, it never happens at the same place. You either have one feature on one end of the world and the other feature on the other world, or the other way around, but not in the same world. So you might ask, well, that's not quite good, because we'd like to have it all in one world. We, after all, know that these things happen in our world, and we don't live in two worlds at the same time. So let's get back a little bit to these stringy models. And these are just a bunch of properties. Yeah, I stopped in the right place. So in particular, in every string theory, again, I was interested not so much in a particular model and how that might work out in a toy model, but what are the generic properties of string theories? Well, all string theories have a well-defined point limit. Otherwise, we wouldn't be able to perceive the otherwise, that string theory is not really useful to describe our world. We know we can describe things as point-like particles. There might be torus compactifications of F theory for those of you who've read the literature. If not, just ignore that comment. There is something called an effective action, which will include the metric, and the usual, this is referred to as the Einstein-Hilbert action, just this letter R here, and one additional term, which describes these things called the Moduli Fields. Notably, these fields do not have any potential, no interaction. These are essentially free fields, except their kinetic energy is not quite the usual one. It's not just sort of 1/2 of mass times x dot squared. There are coefficients in front of it that are a little bit varied. And there is a prescription how those variations have to happen. So in collaboration with Berglund and Minich, we consider the following. Only one of those moduli, which is present in every string theory that we know so far, called the axion-dilaton field. It has a standard dynamics. That kinetic term has to have this thing called the Teichmüller metric. And we made a very simplifying, simple simplifying assumption, saying that let this field only depend on a plane, just two spatial dimensions. See what happens. And in that particular case, we could derive a bunch of useful, nice things. One kind of configuration looks like this, where our world is on this cylinder, and on both sides, in this circle outside and inside, you should imagine another cylindrical sheet around it. And in the other case, there is this sort of the axis of the cylinder is singularity. In other words, we are either on this one or that cylinder. Those are the two configurations we found. Whereas there be dragons in the other places. In other words, those are the singular places. There is where physics goes bonkers. And on this one, this is now a sort of new development by a student of mine who recently got his PhD by showing that in such a configuration, it is possible for a traveler, instead of going inside our world, if the traveler was able to depart a little bit off of our world and travel to those hyper extra dimensions, then they would reach a destination sooner back in our space sooner than another traveler who travels even at the speed of light. So it would be possible to travel faster than the speed of light by taking a little excursion off of our world. So this is the brain world traveler, and the other one is the hyperworld traveler. So this would be a prototype for the jump gate. So there is another thing that these models predict, and let me just quickly run through this. Since there is extra dimensions, there are also Fourier modes, those particles that actually can live in those extra dimensions. But they are really dangerous. They can actually hit particles in our world, and then they obliterate energy momentum conservation. So such things would definitely be bad. But it turns out, well, we must then either ban them or localize them to our space-time. And it turns out that in this model that we discovered, so let me just run through the points. The model that we developed over about 6-7 publications, it is possible, including my student's dissertation, it is possible to do all these things. So we have exponential hierarchy in that model, localized gravity in that model. Moreover, it turned out that we were able to modify the geometry to accommodate what's called the Sitter metric, which has a cosmological constant. You may have heard that the Hubble telescope told us unambiguously we do live in a de Sitter world with a very small but non-zero cosmological constant, and all of that turns out to agree. And there is something like energy loss in the bulk roaming fields that either traps them to our world or traps them away from our world.